Source transformation is yet another circuit analysis tool that is simple and it's very useful in certain situations. So let me cover it. So source transformation simply tells me that these two circuits in here that we saw are equivalent. So what are these two circuits? Well, the first one is a voltage source connected in series with a resistor. Source transformation tells me that it's equivalent or can be converted to a current source connected to the same resistor in parallel. Frankly speaking, it's both ways. If you happen to have like a current source connected in parallel with a resistor, you can convert it to a voltage source that is connected to the same resistors in series. So let me just highlight this fact in here. So this actually is both ways. So source transformation, you can, or source, sometimes it's called source exchange. It tells me that you can convert a voltage source to a current source, but in a very specific situation. A voltage source connected in series with R can be connected to a current source connected in parallel with R. So not any voltage or current source. They have to be in this particular formation. So if these two circuits are equivalent, that tells me, well, if you connect some sort of a load resistor in here, I'm going to call it RL, and then the same load resistor in here, I'm going to also call it RL. They should have the same effect. So regardless of what's on this side, from A and B in here, they should be, if they're equivalent, they should have the same exact effect. What does that mean? It means that the current flowing through this here, for example, let me call it IL, should be the same exact current that is flowing through this here, which is IL. So why am I saying this? Because my goal is to figure out how does Vs and Is relate. So I know the value of R and the value of R did not change, but what does Is relate to IL? Well, or Vs relates to Is. So what I will do is I'll compute IL in here and I'll compute IL and I'll just equate them. That's what I will do. All right, so what is IL from this particular circuit in here with the voltage source? Well, simply I can tell you that IL is Vs divided by R plus RL. Well, you can think about it. Well, what I want is the voltage across both of them, because this one here and this one here, which is R plus RL, should be equal basically to Vs. Anyway, this is just simple Ohm's law. I just combined these two in series, and I just said, well, I know the voltage across them, so Vs divided by R plus RL. All right, similarly in here, we can figure out, well, what is IL? Well, we can use current division in this particular case. It's just simply Is times the other resistor divided by R plus RL. Okay, so now if these two resistors or if these two formations are equivalent, this IL should be exactly the same as this IL. So all I have to do is just combine these two in here, or not combine them, equate them. So Vs divided by R plus RL equals Is times R divided by R plus RL. Of course, this here goes with that. You probably have seen it already. The denominator in here, denominator goes out. Okay, so that tells me that simply Vs is Is times R, or you can also say that the Is is just simply Vs divided by R. So it's very similar. It's not necessarily Ohm's law, but it's very similar to Ohm's law. Actually, it's actually the same in terms of equation. It's not Ohm's law. I'm not applying Ohm's law. What this tells me that if you have a voltage source connected in a series with some sort of a resistor, you can convert it to a current source that is connected in parallel with the same resistor, and this is the equation that you use. So if you have Is and you want to convert to the Vs, that's basically it. All you have to do is just multiply by R. However, if you have Vs and convert it to the Is, all you have to do is just basically divide the Vs divided by R. Alright, so now we know how source transformation works. Let me show you an example of how to use it very, very quickly. So here's a circuit in here, and in this particular circuit we were given, well, compute the V0. So you take a look in here. Well, of course, there's multiple ways to solve it. You can just tell me that this is my reference node. I'm going to figure out what this node voltage is in here, and based on that, I'm going to use voltage division just to use that. You can definitely do that, or maybe you're going to write mesh current. That's fine. But another tool is the following. Look, I have a current source in here connected in parallel with some sort of a resistor. I probably can just convert this into a voltage source connected to the same resistor, which is the 1.2 kilo ohms. You see, it's like the beauty of it. I don't have to compute the value of the resistor. It's the same one, and it's different than the 1.2 that is already on the circuit. This is the 1.2, and I have the 1.8 in here. Okay, this is 1.8 kilo ohms, and the voltage source, really simply, the Vs value is just simply Is, which is 3.5 times 1.2, the R. That's what you have to do. So you multiply 3.5 times 1.2, and you will get the value is, I believe it's 4.2 volts. So that's the value of that particular volt. So you can convert. Sometimes it's the opposite. Like for example, you can convert these two, or you can combine these and convert it to a current source. But anyway, what we're being asked to compute is what the value of V0 here is. And of course, you have probably seen it by now. These resistors are in series, and I have voltage source across them, and I'm interested in one of the voltage. Well, all I have to do is just use voltage division to do that. And you can use the rule for voltage division, and that rule would be V naught, the one that I'm after, is just simply 4.2, that's the source, times 1.8 divided by the series connected resistor, which is 1.2 plus 1.2 plus 1.8. And that would be equal to, I believe it's 4.2 volts, okay? So we were able to use source transformation to quickly figure out that this is 4.2 volts, okay? This is a very simple circuits that we can use. All right, now that's how we use source transformation. However, I just want to mention a couple of things in here. For example, source transformation is not a generic tool that you can use all the time. For example, in this circuit in here, if I'm been asked to compute V naught, and you take a look, well, I have a couple of sources in here. I have a voltage source and a current source. And if I told you, like, hey, use source transformation to solve it, you won't be able to. And the reason why is the following. Source transformation applies to the following. A voltage source connected in series to a resistor. Well, this resistor is not connected in series with that because I have that wire coming in here. So they don't only share the node, like basically this node is shared by a different element, which is, for example, the 6 kilo ohms. And the same goes with the 2 kilo ohms. It's not in series with the 6 volts. So technically, I can't use the 4 and 2 to convert. I can't convert this into a current source. Similarly, I can take a look at the current source in here. I don't see any resistor that is connected directly to it in parallel. Like there's nothing that shares just two pairs of nodes. So I can't use source transformation to convert this particular current source into a voltage source. So source transformation for this particular circuit is not very useful. And another issue with source transformation is the following. So in this particular circuit, I have dependent sources. As it turns out, while technically you can use source transformation to transform dependent voltage sources, it's a little bit tedious because you're going to have to track like where's the dependent current, or where's like my controlling current or my controlling voltage. So while you technically can use it, we are trying to introduce it as a simple method to basically an addition to circuit analysis method that we're using, but to simplify things, not to overcomplicate things. So with dependent sources, let me just give you an example in here. So let's assume, well, I have this two source for this voltage source is connected in series with a resistor. So technically I can convert it. I can also convert these two in here, which is a current source connected in parallel with a resistor. So let me just redraw the resulting circuit after the conversion without worrying about what the value is. I mean, I can figure out what it is. So here's that voltage source. I need to figure out what that IS is. And of course, this here is still 5 ohms because it's still the same R. And of course, I have another one in here. This is the 20 ohms because what I did is now I just converted these two. They became in parallel, like a current source and a resistor. And of course, it stays the same. So we still have to redraw it. And I have a current source in here, and that will be 0.4 V delta. And then I have the V delta in here, which is 10. Oh, well, here it's going to be converted. Okay, so let me just do that. Okay, that's plus minus 2 I delta. That's basically the voltage source. Well, this current source in parallel with the resistor will be basically converted to a voltage source in parallel with or in series with the same resistor, which is the 10 ohms. Okay, and I'll have to figure out what the VS is. It's basically VS should be just 50 volts because it's 5 times 10. That's what it is. And this one here is simply like if I'm to compute it, IS will be I believe 10 divided by 5, which is just simply 2 amps. Okay. All right. So now that's fine. Why am I drawing this? Well, this here depends on V delta and this one here depends on I delta. And as it turns out, by doing this conversion, these V delta and I delta disappeared because the I delta was the current flowing through the 5 ohms when it was in this particular formation. It's not the same I delta in here. This is not I delta. Yes, I still have the 5, but this is here is not I delta. So I delta disappeared. So now this dependent voltage source, I don't know what it depends on. It basically disappeared. So I technically couldn't do this transformation. The same goes with the V delta. The V delta was across that 10 ohms. Well, the 10 ohms moved now. It's not the same. So the V delta moved. This is not V delta here anymore. So I don't know what this depends on. So that's why with dependent sources, while you technically can use source transformation, you probably should avoid it.